We're moving on now to a new topic, that of logic, which is covered in chapter 5 of the textbook. So you might be wondering why on earth we would be studying this, and to get a feel for it, we're actually going to have a very brief tour of the history of logic. So when we talk about logic, we're meaning the study of reasoning conducted according to strict principles of validity. And this actually has a very long history in a number of traditions across the world. For example, in India, the study of logic developed in around the 6th century before Common Era and was further developed until well into the 18th century and is in fact still studied in various places in the East today. The Chinese school of logic was very well developed in around 400 BCE, but it was repressed during the Qin dynasty around 200 years later. The logic that we're going to study was initially developed by the Greek philosopher Aristotle, who lived around 350 years BC, and he wrote a book called Prior Analytics, which is just really a collection of rules for how to go about doing deductive reasoning, and it was intended as a logical basis for pretty much anything you would want to study. And in fact, these rules are still used by scientists and doctors and lawyers today. In around the 1700s, Western logic got developed a little further by a bunch of famous mathematicians. You'll probably recognize some of these names, in particular George Boole, from which we get the word Boolean, and you've probably already come across Boolean logic if you're doing computer science. And what these mathematicians and many others did was they took the deductive rules of Aristotle and they turned them into symbolic logic, which they further developed. And it is symbolic logic which is really mathematical and which we're going to study. Where does logic crop up today? Well, it's the theoretical basis for a number of things, including digital logical circuit design. If you do anything to do with relational databases, you need to know about it. If you work with automata, then you're going to be using symbolic logic, and both artificial intelligence and computability require a symbolic logic. So it underpins a lot of the computational work that's done today. So how do we start? Well, the basic idea in logic is the idea of a proposition, and it's a sentence to which one and only one of the terms true or false can be meaningfully applied. So, for example, the statement 4 is even is a proposition because either it's true or it's false. In this case, it happens to be true. So this is a proposition. Now, the statement 4 is an element of the set 1, 2, 5 is also a proposition because it's either true or false. But this one happens to be false. We can also have more complicated propositions. For example, Europa supports life or Mars supports life. Well, although we might not know the answer to these, this is definitely either true or false. So this is a proposition, but we don't know yet. So you might be thinking, well, is every sentence a proposition? No. For example, if we look at the sentence, close the door, that's a statement, but it's not a proposition. It's neither true nor false. Asking questions such as, is it Monday, is also neither true nor false. And then we also can look at some mathematical things which are not propositions. For example, if we consider this sentence, this says x is greater than 2 for x as element of real numbers. Well, this is not a proposition because it could be true and it could be false depending on the value of x. Now this is a statement, and you might think, well, obviously it's always true, but the way we're going to think about it in terms of logic is that this is a declarative sentence, but unless x is actually assigned a value or is otherwise prescribed, it's neither true nor false, so it's not a proposition. So there we have some examples of the basic things that we use to develop logic. So how do we develop this into a mathematical system? Well, we usually assign a variable name to a proposition. So for example, if our proposition is 4 is even, then we will give it, for example, the name P1. And then we can start to say if P1 is true or P2 is false. And to again bring more maths in, if the proposition is true, we're going to give it a value of 1. And if it's false, we're going to give it a value of 0. So here we have P1 is true. If we let 4 as an element of 1, 2, 5 be the proposition P2, then we have that P2 is false. So we call that 0. And we could call this complicated sentence Europa supports life or Mars supports life. We could call that P3. And if we did some research, we could figure out whether P3 is equal to 1 or 0. And we've already said these are not propositions, so we're not going to assign values to them. Now you'll notice that we had two pretty straightforward sentences and then a more complicated one. So it's useful to define what's called an atomic proposition, which is one whose truth or falsity doesn't depend on the truth or falsity of any other proposition. The idea is that basically we want to be able to break up any statement into individual tiny little propositions that stand by themselves. For example, 4 is even is an atomic proposition. We can't break it up any further. Similarly, 4 is an element of 1, 2, 5 is atomic. But if we look at the sentence Europa supports life or Mars supports life, well, we could break this up into a smaller proposition, Europa supports life, which is either true or false, and Mars supports life, that's also atomic. And then when we combine them together by use of the little word or, we're going to get what's called a compound statement. We do this breaking up because it makes it easier to decide the truth of a compound statement if you first know the truth or falsity of an atomic statement. Alright, so we've got our simple statements, which we're thinking of as our atomic statements, and we combine them into compound ones using several different words. The most common words that we use are things like and, or, not, if then, and if and only if. And by combining atomic statements using these connecting words, we get new propositions. So we're going to talk through each of these in turn. Now, one of the things that we can do is we can say something is not true, but all the other operations that we have act on pairs of propositions. So, for example, if we're thinking about and, we've got proposition 1 and proposition 2, and so on. And each atomic proposition can either be true or false. So there are 4 ways that truth can be assigned to 2 propositions. So we end up having to define the effect that a logical operation has on 2 propositions in 4 cases. And we're going to call those cases, we're going to write them out as a logic table. We're going to start by looking at the word and, but first just want to introduce the connectives that we're going to use. So whenever we want to talk about and, we'll use this funny symbol here. Occasionally in texts you'll see either an ampersand or a dot. We're also going to introduce the connective or, which looks like a V, and occasionally you'll see that notation, but we won't be using it. If you want to say that not a proposition, we'll use a little corner like this, and occasionally you'll see this twiddle here. If we want to say if proposition A implies proposition B, we'll use a sign like that, and occasionally you'll see those. And then finally, if and only if uses that symbol there. But we're going to start by looking at and. So when we're talking about and, we're talking about logical conjunction. So this is the idea of combining two atomic propositions using AND. So if P and Q are propositions, their conjunction, which we say P and Q, and we denote it like so, is defined by the following truth table. So the first time you see a truth table, you might be wondering what on earth is going on here. And remember we said that each atomic proposition has two possible values, true or false. And so when we want to figure out all the possible values for P and Q, we need to have 4 possible cases for each of the different combinations of the truth or falsity of P and Q. So that's summarized here. To read this table, you must realize that any one line represents a case, one possible set of values for P and Q. So for example, if we have a look at this first line over here, if our first proposition is false and our second proposition is also false, then it turns out that P and Q must also be false. This makes sense if you think about it. We'll come to an example in a moment. So as we've said, our numbers 0 and 1 are used to denote false and true. And if you've done any programming, you'll find that most programming languages use Boolean variables where 0 and 1 can represent the truth value. 0 for false, 1 for true. So here, in each column, we're saying what value we're taking for that particular atomic proposition. And then in the next column, we're giving what the value of P and Q is. Just a note, the order in which we list the cases in a truth table is fairly standardized. And we increase as if we're writing binary numbers. So we've got 0, 0, 0, 1, 1, 0, 1, 1, which in binary is 0, 1, 2, 3. Okay, so let's think of an example of 2 propositions and then combine them and see if this makes sense. So here we've got 2 compound sentences, and let's break them up into atomic propositions and then figure out the truth. So here we've got 3 as a prime number. Let's call that atomic proposition P. And we've got 2 divides 6. That's also atomic. And we can now think about their truth or falsity. So if we think about, is P true or false? Well, 3 is a prime number. So we will say that P is true. And 2 does divide 6. So this is also true. And so if we combine, if we want to think about P and Q, since both of these things are true, our overall compound sentence, 3 is a prime number and 2 divides 6, is true. And if we go back and check our table here, when both our atomic propositions are true, then the result of combining using AND is true. Both things are true, so this and this is true. Just to give a different idea, so you see that it doesn't always work like this, let's keep the same initial atomic proposition. So we've got P here, but we want to let 2 divides 7 be our next proposition. And here by divides, I mean without remainder. In this case, S is false because 2 doesn't divide 7. And so we're combining P and S. And here our first thing is true, but our second thing is false. So combining with AND, we have that these are false. It is not the case that 3 is a prime number and 2 divides 7. And just going back to check our table, if our first thing is true but our second is false, then the whole thing is false. And in fact, looking at this table, you'll notice that the only time when logical conjunction is true is when both of the atomic propositions inside it are true. If they're both false, then logical conjunction is false, and if only one of them is true, then it's false as well. So let's look at the kind of opposite, if you like, logical disjunction. So logical disjunction is when we're talking about combining atomic propositions using or. We're talking about P or Q. And it's worth noting here that this is a little bit different from the English or that we use. And I'll explain why in a moment. So let's have a look. Mathematically, we use this V sign, and our truth table says if our first statement is false and our second statement is false, then P or Q is also false, which makes sense. On the other hand, if I have one or both of my statements being true, then P or Q is true. So this is where English and maths are a little bit different. In English, we would say, well, I would like pizza or a hamburger for dinner, and I'd expect to get one, but not both. But when we're using logical disjunction, we have the situation where P or Q is also true. So English, we usually think about one or the other as being true, but here we can have both things also imply that or is true. So let's have a look at how this works if we've got our original atomic statements. So again, we've got 3 as a prime number. We're going to call that a statement P. 2 divides 6, which is true. And we want to think about P or Q. Since these are both true, then P or Q is true, because if one or both of the statements is true, then logical disjunction is true. If we compare again with our slightly different version, so again we've got 3 as a prime number, which is true, and we have S is our statement 2 divides 7, and that's false, but now we have P or S is true because we do have one of them which is true. Now we mentioned that there was a possibility of wanting to say that some statement is taking its negation or saying not P. And to do that, we just take the particular proposition and we put this little square before it. So if we look at our truth statement, if P is false, then not P must be true. And if P is true, then not P must be false. So for example, if we say that our first statement is 3 as a prime, then we have that this is true. So this says not P, i.e. 3 is not a prime, is false. On the other hand, we had 2 divides 7. We said we'll call that S. Here, 2 doesn't divide 7 without remainder, so S is false, but not S, which says 2 does not divide 7, is true. So those 3 connectives, logical conjunction, disjunction, and negation, form the basis of logic. And in the next video, we'll explore some more compound statements using other connectives.